Hi, so in our campus this year, we're gonna be having science journals for the 4 oldest classes. The littles, they don't know how to write. We decided we'd do something different for them, some coloring sheets and stuff. But for the 4 oldest classes, we're gonna have science journals this year. So each student will have a journal and a cover page, and the first week you can go ahead and let them cut it out to size, write their name on it. We'll let them glue it on the front, and if we have time, they can color it because that first day might be a little light. If they don't have time, at least get it glued on and get their name on it so that we can get started right away if there's stuff we need to do for the first week. The importance of a science journal. So my husband is a scientist, he works for 3M, and every single day he uses a science journal just like this. So I think it'd be fun to talk to the kids about that in real life, scientists use science journals every day. And what they do is they write down their observations, they write down hypotheses, and they mostly write down the conclusions, what they found out, what they figured out after they saw their experiment. So since we'll be short on time, in our community this year, we will mostly be writing down a hypothesis for the older kids and then our conclusion. So that'll look like a picture for a lot of kids, that will look like a sketch, a quick drawing, maybe a sentence or two. But what we're gonna do is we're gonna each week that we're gonna use the science journal, it'll be referred to like draw a sketch in your science journal about what happened. But I think it would be important to talk to the kids about that this is something that they're gonna use in challenge as well. So challenge students are graded on how their science journal is set up and the way they go through the method, the scientific method in a proper way. And so talk to them about how they're setting up kind of a good habit of being a scientist. So we can get kind of excited about it, and we've done an index before this year for the older classes. If you want to just do an index, a simple index on the front page, you can. For the littles, I'm probably just going to have them start on the first page, and we'll just write the title or what the name of the experiment that we're doing, and they can write a page number or something if they want to refer back to it. We're going to try to make it look as official as possible, but then mostly, I'm guessing for most kids, it will be a sketch or a simple sentence or two. So that's what we're going to do for the science journals.
Hi, this is Cycle 2, Week 1. We have 2 experiments to do today, and you get to go outside. So the first one is number 2, shaded, and your supplies are going to be 2 thermometers, and the type of thermometers I have here have mercury inside, so we need to be very careful that they don't break because they're actually toxic. We do have to purchase a few more, and we might purchase ones that do not have mercury, and you should be careful with those too. But 2 thermometers per class, and then you're going to have a couple different images today, but for this first experiment you're going to use this page right here. And this one, I have it labeled underneath, is the landscape of Mars, and this one is Mercury's, part of Mercury's landscape called the Caloris Basin. So you'll show that about midway through the experiment. Now, since this experiment is going to be outside, there's always a chance it's raining or it's not sunny and it's cloudy, and we need sunshine for this to work. So if the weather is not in agreement with us, then we will have to bring a lamp like this. I do not have lamps for us, so we will have to find some. Hopefully you have one at home that you can bring, or another tutor has one at home that they can bring for you. But we will turn it on. And I brought this from home because this is what I had. You can definitely use like a tin can, you can use anything that's kind of gonna make it so that the sunshine, so the lamp is gonna be the sun. And we need the sunshine from the lamp to hit the thermometer to give us an accurate reading. And then we would put the second thermometer behind the bin where it's in the shade. Okay, so that's what we're gonna have to do inside. Ideally we're outside because that's gonna make it a lot more lifelike and real. So we'll see how that works. So those are your props. The purpose of today's experiment is to determine or to demonstrate how a planet's surface temperature can vary. Okay, so because it's week 1, we're going to go over the scientific method in a little more detail than we will in other weeks. Which is why I have it first on your script, to kind of go through like what is asking a question like, doing some research, what does that look like? Is it stuff you already know, or is it stuff you still need to find out? Developing a hypothesis, letting them tell you what they think a hypothesis is, and then down through experiment analysis and conclusion. It's all here for you. Once we've kind of gone over that, you want to make sure you sing the song, which is also in here for you. And then you're going to have a few questions. You're going to talk about some research. I have all of some ideas for how your kids could answer in red. And then you're going to determine the hypothesis. What do you think? Can separate surfaces on Earth, as well as possibly other planets, be different in temperature? Okay, so all of this is still in the classroom. You have not gone outside yet. The kids are going to have to determine what kind of tool they should use to measure temperature. They can't just go outside and feel it to know a direct number or a degree. They actually need to use a tool called a thermometer. Okay, so then when we get to the procedure part, that's when you tell them that earlier today, or earlier that morning, 2 thermometers were put on the ground in different places outside. Okay, I can do that for you when I first get there in the morning. We're going to be on the back side of the church, and I'm going to place 1 of your thermometers in the sunshine and 1 in the shade. I will most likely be using the building to act as the structure to create the shade. If for some reason I cannot find enough shade with that, I might use a tree. I will send you a Voxer message to let you know which one I use, but hopefully there'll be enough shade from the building to make it work. Okay. It is important to note to your students that we need to control variables to make it scientific, to make our experiment more valid. And so one of the ways we can control variables is by putting it on the same surface. So I'm not going to put like 1 on the grass and 1 on cement. I'm going to choose either grass or cement, and both are going to be on that same surface. Okay. Another way you can control the variables is by telling them that you checked, or I checked, to see that both thermometers were laying down read as the same temperature before you place them in separate locations. Because if one reads very differently, then it could mean that one is broken, or it could mean that one just isn't working right, and therefore it's not going to give you accurate readings. So after you've told them that, it's time to go outside. And that's when you'll take them out, you'll find them, you'll collect both of them, you'll kind of gather your class in, and you'll do your analysis. And we'll be able to say, okay, the thermometer in the sun reads this, the thermometer in the shade reads this. It's about an average of a 15-degree difference in the shade and the sunlight if it's direct sunlight. It should be about 15 degrees different. Okay? And then you could even ask them, which thermometer showed a warmer air temperature? Okay? And then part of this is determining, like, this is how temperatures can vary on Earth, but what about other planets? Are there structures on other planets that could provide shade where temperatures vary in one location from another? And the answer is yes. And so then that's when you can show them these pictures. This top one is kind of like a big sand dune ridgy type thing. And you can actually see the shade in this area. So this big sand dune or this big ridge is providing shade on this side for lower temperatures. And then down here, you can kind of see there's lots of different levels. There's lots of topography pieces to this. But some are going to create more shade and some are going to let the sun hit it more directly. So you can show them that, and you can talk about other planets. And then, so when we go through why did we observe what we did, a lot of that will be for the older classes. It's kind of about how energy transfers into the thermometer and how heat makes liquid particles move faster than colder temperatures, and I don't know how much the littles will get of that, so you can read through this and kind of just determine if the ages in your class will understand it. Alright, so we're going to move on to experiment number 2. It's number 17, and it's called Same Place. I do have a suggested video at the top for you. I think that would be good to save until the end, just to see if you have time. If you run out of time, you can send that home to your families, and they could definitely watch it at home. It is really informative. It's just about 3 minutes long. Please note that it does talk about satellites that move. It doesn't specify geostationary satellites, which is what we are talking about today, but it's still really helpful information, and it has lots of good visuals. So the props that you will need today for this experiment are rope, and it's going to be about 3 yards long. Okay, and then I have lots of pictures for this one. So I have a picture of a satellite orbiting Earth here. I have a picture of the moon, and I have these all labeled. The moon orbiting Earth, because our moon orbits around our Earth, but then our Earth orbits around the sun. And then here's just kind of a diagram of them both doing that at the same time. So you have your pictures, and then you also are going to have this marshmallow model. And the big marshmallow is Earth, and the small marshmallow is a geostationary satellite. So in the middle of your experiment, I cue you in here. You're going to be able to kind of turn it, and what the kids will be able to see is that geostationary satellites keep on the direct path that Earth does. So actually, from the position of the satellite, you're going to see the same thing on Earth. The Earth isn't even rotating, because they're just looking at the same thing as it goes around. Okay, so you have a little intro here, talking about the Earth rotating on its axis, talking about satellites, how you can sometimes see them in the sky, talking about what the word orbit means, okay, and then we kind of go into, there's different kinds of satellites. Some are made by people, and some are naturally part of God's creation. We already talked about the moon and the Earth kind of being natural satellites, but how we are going to talk about geostationary satellites today, and why it's important that they rotate at the same speed as Earth. Okay, so the question we're asking today, or the question we're answering is, if satellites move, why do some appear to be stationary? Okay, this is a fun one because you can kind of get your class to show hands, to just really get involved and answer lots of questions and kind of chime in on what they think. So you're going to need 2 volunteers, and I forgot to say, you're just going to stay outside for this one. You're not going to go back in the building. So you're already outside after you read your thermometers. You're going to set those aside, and you're just going to stay right where you are, okay? And then you're going to call for two volunteers, and the first child is going to be representing Earth, and they're actually going to stand right under a tree, kind of like with their back to the trunk. If this is the tree, they're going to be standing with their back to the trunk. And they're going to hold one end of the rope. Then your other volunteer is going to hold the other end of the rope, and they're going to stand directly straight out from them. We want it so that the rope is taut. We don't want any slack in it, but we also don't want them pulling it so tight that they're going to pull volunteer 1 out of orbit. Okay? So, volunteer 1 is acting as the Earth. Volunteer 2 is going to act as the geostationary satellite. And since we can't really get it all in range here on the video, we're just going to do a short one, okay? So here's Earth, volunteer 1. Here's the satellite, volunteer 2, okay? Here's the tree behind me. So if I'm volunteer 1, I'm going to start taking steps with my back kind of stuck to the tree. I'm going to rotate around the tree, taking steps as I go. Volunteer 2 is going to have to keep in line with me the whole time, keeping the rope straight. And the point of this is that they're going to see that volunteer 2 has to take so many more steps to stay in line with volunteer 1. Their circle is so much bigger than volunteer 1's circle, who is just circling the tree. Okay? And so that is going to point out to them that satellites need to move so much faster than Earth to be able just to keep up with it. Okay, so after we do that, you can ask things like, what do we observe? How many steps did the second helper need to take in order to keep up with the first helper? Which helper had to go faster? Was our hypothesis correct? Things like that. If time allows, it might be fun to have another set of kids be volunteer 1 and volunteer 2. They might have fun with that, okay? You can go over your conclusion, you can go over what you observed and why you did, and then I have a summary and a scripture interpretation at the end. I think that's all.